All right, let's talk about one of the coolest tricks in all of electrical engineering, Norton's theorem. You know, if you've ever stared at a circuit diagram that looks like a bowl of spaghetti and just felt totally lost, well, you're going to love this. We're going to see how to take that chaos and turn it into something beautifully simple. I mean, just look at this thing. What a mess, right? You've got current sources, voltage sources, resistors everywhere. Trying to figure out what's happening at those two little output points, A and B, seems like a nightmare. And here's the real kicker. What if you want to connect something new to it? A new motor, a different sensor, whatever. Are you seriously going to redo all those crazy calculations from the very beginning? Every single time? No way. There has to be a better way to do this. And that better way, my friends, is Norton's theorem. I absolutely love this analogy. It's perfect. Forget about all the complicated ingredients inside the box. The theorem just gives you the simple, need-to-know summary of what that circuit can actually do for you. And this right here, this is the big promise. On the left, you've got that complicated black box. And on the right, that's what Norton's theorem lets us turn it into. It's a total game changer, and we're about to see exactly how it works. So here's the official definition. It says that any linear circuit, and that just means a circuit with stuff like resistors, where the output is proportional to the input, can be boiled down to just two things. That's it. A single current source, we call it IN, sitting right next to a single resistor, RN. Simple, elegant, and unbelievably useful. And getting there is surprisingly easy. It's just a two-step process. First, we've got to find the value of that current source, IN. Then we find the value of that resistor, Rn. So let's just do it. Let's take our example circuit and walk through it. All right, first up, let's get our hands dirty and find that Norton current IN. You can think of this as the absolute maximum current that our circuit can possibly push out. So to find it, we do something that feels a little dramatic. We literally just take a wire and connect it straight across our output terminals A and B. We create a short circuit. And the Norton current, well, it's simply the amount of current that flows through that new wire. That's why it's also called the short circuit current, or ISC. Okay, now we just need to solve for that current. We're going to use a classic technique here called mesh analysis. If you look at the first loop, it's pretty simple. The current I1 is just dictated by that 2 amp source, right? So I1 is 2 amps. Now for the second loop, the one with our short circuit, we use Kirchhoff's voltage law, which gives us that equation you see. Since we already know I1 is 2, we just pop that value in, do some quick math, and solve for I2, which is our short circuit current. And what do we get? 1 amp. Just like that, we've got the first piece of our puzzle. Our Norton current, IN, is 1 amp. Boom! Step 1 done. All right, 1 down, 1 to go. On to the second and final piece, the Norton resistance, or RN. This basically tells us what the internal resistance of that original messy circuit looks like from the outside. Now, to find this, we pretend to look back into our terminals A and B. But first, and this is super important, we have to turn off all the independent power sources inside. Here's the rule. Current sources get replaced by an open circuit, like just cutting the wire, and voltage sources get replaced with a short circuit, just a plain old wire. Once the sources are gone, we're just left with a simple network of resistors. So, looking in from A and B, what do we see? We see that 5-ohm resistor is in parallel with everything else. And that other branch? It's just the 8, 4, and 8-ohm resistors all in a nice straight line. That means they're in series. So we just add them up. 8 plus 4 plus 8 gives us 20 ohms for that whole branch. So now the problem is simple. What's 5 ohms in parallel with 20 ohms? You run the calculation and you get our final answer, 4 ohms. That's it. Our Norton resistance, Rn, is 4 ohms. We have both pieces we need. Now for the best part, the grand finale. We've done the work, we've found our two magic numbers. Let's put them together and see the payoff. And there it is. Seriously, look at that. That tangled mess from the beginning has been totally replaced by this beautiful, simple circuit, a 1 amp current source in parallel with a 4 ohm resistor. From the perspective of anything you connect to A and B, these two circuits are exactly the same. How amazing is that? And this is why it matters so much. If you want to connect a new load to your circuit now, you don't have to deal with that complex beast anymore. You just connect it to this simple version and the calculations are a piece of cake. You've just saved yourself a ton of time and potential headaches. Now, you can't really talk about Norton without mentioning its famous twin, Thevenin's theorem. They're a duo. While Norton gives us a current source in parallel with a resistor, you could call it the current view, Thevenin does the same thing but with a voltage source in series with a resistor. That's the voltage view. But here's the really cool part. They are literally two sides of the same coin. A Norton circuit can be easily converted into a Thevenin circuit and vice versa with a simple trick called source transformation. This gives you incredible flexibility as a designer to pick whichever model makes your life easier for a given problem. So there you have it. We took something that looked hopelessly complex, and with just 2 simple steps, we tamed it. We found the simple, elegant truth hiding underneath all that mess. This is the real power of tools like Norton's theorem. They make the impossible possible. So the only question left is, now that you have this power to simplify anything, what are you going to build with it?